Hi, we now switch our attention to the curves in general metric spaces. As you can see, we have already covered the notion of rectifiable curves in Euclidean spaces, and we've talked about when the length formula, which we will see in this slides as well, holds for such curves. Please do check out those videos. And by the way, if you have been following my lectures but have not yet subscribed, please consider doing so. That is the best way you can help me. Well, let's recall, just for completeness, what a metric space is. It's only a set, and the only structure on it is a distance function, which precisely is a function from x times x to non-negative real numbers, such that it's non-degenerate. It's zero only if you are measuring the distance to itself. It's symmetric, and the most important one, the triangle inequality holds. Whenever you bring in a third point and you compare the distances, you only go larger and never smaller. To emphasize, there is no other structure on the space, especially no linear structure. There is no notion of adding 2 points. There is even no notion of 2 times x in such a space. Any subset of a metric space is again a metric space, which emphasizes again that these are pretty relaxed conditions, and just compare it to having a linear subspace. It must be huge, for example. Any scaling must be again in the subspace so that it remains a linear subspace. But with metric spaces, just pick any subset of your space you wish. With that same distance, it is again a metric space on its own. Metric spaces are not the weakest spaces. Topological spaces are even come even with less structure, let's say. So the open balls, which are defined in the obvious way, form a basis of the open sets for a metric space. So it is a topological space, and it makes sense to talk about continuous maps from X or into X. But for example, it doesn't make sense to talk about C1 maps, because that requires linear structure. Many of our familiar spaces, Euclidean spaces, Hilbert spaces, Banach spaces, manifolds, sub-Riemannian manifolds, and any subsets of them are examples of metric spaces. So it is very desirable to have something proven in the generality of metric spaces, so that first, it applies to all these special cases, and number two, we can appreciate what is being used in a certain theorem, or what a particular theory depends on really. The definition of a curve as a continuous map from an interval makes sense. Also, the notion of a Lipschitz curve makes sense, because that only uses the notion of distance. And as I had promised before, the definition of length and rectifiability is exactly the same. I literally copy pasted that formula because I didn't want to type all of these. And I replaced this norm of gamma of ti minus gamma of ti minus 1. Actually, I had forgotten to initially to replace it with just distance. Okay, so all of these make sense. And most importantly, this arc length parameterization theorem holds. I refer to the first video of this series for more in-depth discussion of what is going on in these reparameterizations, and more details about arc length and whatnot. But the key point is that if you have a rectifiable curve, then you can reparameterize it by a new curve, gamma 0, that is a much better curve. And the much better is contained here, that it is parameterized by arc length. The length of this new curve in the time interval, say 0 to s, is exactly s. It travels s feet in s seconds. And we have been talking in detail about this. Again, go check out that video, and also mentioned how it is proven. For completeness, this is the meaning of what do we mean by an increasing change of parameter. And you can forget all of that and just know that this gamma 0 is a one Lipschitz parameterization. And Lipschitz parameterizations are very important. Even in the Euclidean case, we saw that the length formula holds for them. Excuse me. And actually, we will now switch only to the one Lipschitz case, especially in light of this theorem. There is no loss of generality in doing so. Okay. Our next goal is to find an analog of the length formula from the Euclidean curves. We had this formula, and it was true if and only if gamma was absolutely continuous, which contains the case of Lipschitz curves. The first thing that we should answer is, what do we replace this with, right? This is already defined, but how about this? Well, let's recall what gamma prime is. You, by definition, if your gamma is differentiable, then this limit exists, and gamma prime is the limit of that. This is a vector. This is a vector in RD. Their subtraction is a vector, and you divide by a real value h. So we scale that vector, and things go, and then you take limit. And none of this makes sense. So subtraction doesn't make sense. And even if you have an element in the metric space, dividing by a real number doesn't make sense. So is there a way out? Well, we notice that if we take norm, then we have this limit. And this is an exercise that if a sequence of vectors converges to another vector, then their norms converge to their norm. Okay, exercise, that's a cute one. So in light of this exercise, we have this. And now we notice that this is just distance of gamma from gamma at t plus h versus t. Well, I have it typed up, so why not show it to you? So this is just the distance. And now it's a real number, so I can divide by another real number. So this all makes sense. Therefore, we define for a curve that goes into a metric space this quantity, this limit. And when it exists, we say that our curve is metrically differentiable at t. T is fixed, h goes to 0. And if we work backwards, if you have a curve into RD, and if it is differentiable in the usual sense, we see that this limit actually exists and equals this. Also, some terminology from physics is helpful. This is a velocity. This is how fast the object is moving, and also in what direction. So that is gamma prime of t. But this is speed. This is just a number. So in the metric context, we don't have this, but we have this. So there is nothing called gamma prime of t, but there is something called its norm. So we didn't find the replacement for gamma prime, but we did find the replacement for this whole package. Of course, this is only a definition, and whether a curve is differentiable or not, that's a different question. There's also the tricky notation that if this limit exists, we denote it by this. And this is, well, to compare or to, this notation is based on what we have in the Euclidean case, but also it can be confusing. Again, there is no gamma prime, so we're not talking about gamma prime, but this whole thing is one notation. You could also pick any other thing. For example, metric derivative of gamma at t is a less confusing notation. So just remember that this is meaningless, only a notation. Okay, the most important theorem which guarantees why we define this arbitrary thing, seemingly arbitrary thing, is that if you have a Lipschitz curve, indeed it is differentiable in that sense almost everywhere, Lebesgue almost everywhere, right? So this gamma prime t exists at almost every t, so this is defined almost everywhere. We can integrate it, and surprise, the length formula holds. This is from Ambrosi and Tilley's book that I mentioned in the references. The book's title is an analysis on metric spaces. I may be a bit wrong, but analysis on metric spaces is the core title there. And this has about a 2-page proof. So very well worth checking out. I want to give you an example. My next video will be dedicated only to examples, and I will do a lot of them. So you will see more of this metric derivative. But for now, I give this a bit surprising thing that if you are traveling the curve t gamma t in R2, say in this direction, as t goes up, then this is differentiable even at 0, despite this visual break. The reason being that when it comes to distances, this curve doesn't see a bend. So distance of that to that would have, and this, the alignment of these would have been the same if this was here. Like this, well, I intended to do it like a y equal x curve. Okay. This red and this blue are the same when it comes to distances to the origin. That's why when you want to compute this gamma t plus h, well, 0 plus h and gamma of 0, it is as if it was the straight line. So after all, it's an explicit formula you can write down for yourselves and then prove that this indeed the limit exists. And whenever it does, it's √2, and that is because from t to t plus h, this will be h, this will be h, so here will be √2h. So distance of gamma t plus h, gamma t divided by h is √2h. Again, h could be negative. So that's √2. So when you take a limit, it's again √2. And according to the length formula, then length of this curve between any AB should be √2 times b minus a. And this includes the case where a is negative, b is positive, or of course, any other cases as well. That's the only interesting one that passes through the 0. Yeah. We see here that a curve may be metrically differentiable even when it is not differentiable in the usual sense. Of course, differentiability in the usual sense asks for velocity, and that was what is missing in the break, but with the speed, it is not there. Okay, so I want to finish by this, just mention that a much deeper theorem due to Kirchheim from 1994 claims that Lipschitz functions from any Rn, not just R1, which is the interval. So we did this case, but that theorem says that even if you are in an arbitrary Euclidean space, in a deeper sense, the functions are differentiable. That deeper sense is that if you take kind of partial metric derivatives, so in every direction, it becomes like a curve map, and we have metric differentiability. But the point is that these metric derivatives in all directions bundle together into a semi-norm. And that semi-norm is called the metric derivative of such a function. And this theorem was the starting point of a lot of things, deep things really, in metric spaces. Basically, it allowed geometric measure theory to be done in the setting of metric spaces. I spent my PhD, a good deal of it, on that theory. What we did, it had been done, but we also did new stuff in the questions of area formula and co-area formula using this metric differentiability in the sense of Kirchhoff. But anyway, that's not what we are going to talk about in this series. Maybe in future. So again, as a teaser for my next video, we will do some metric derivatives, some more geodesics, and this will be more specific examples. For example, in R2, if you equip it with the L1 norm, what the geodesics look like. If you have R2 with the L infinity norm, what are geodesics then? Geodesic is the shortest curve. We will see some surprising things in these. Until then, have a great one, and don't forget to like and share my videos. Thank you so much.